all. In today's session, we learn about how to design a magnitude comparator circuit. So generally, the magnitude comparator function is to compare your given two numbers of n bit. So now that nth bit will be a 1 bit, might be a 1 bit, a 2 bit or n bits also. So now generally it is having two inputs with three outputs. So these two inputs are specified with your number of bits. Based on that, we will have your the number of inputs are increased. So now if it is 1 bit, then it is called as a 2-bit comparator. If it is having your 2 bits, it is called as a 4 inputs. If it is 3 bit, it is having the 6 inputs. Like this, the comparison is done with the bit by bit comparison, started with the most significant bit position to the least significant bit position. Now in this magnitude comparator, we are going to check your given number, first number with the we are comparing with the first number with the second number b. Relative magnitudes we need to compare, and based on the relative magnitudes, so one of the output will be equal to logical one. So now we start with your most significant bit position and moving towards to the least significant bit position. At each bit position, we are going to check whether your given number, first number, is greater than the corresponding bit of your second number. Then a greater than b output is set to 1, and the circuit immediately determines that the first number is greater than that of your second number. Similarly, if the bit of your second number is greater than the corresponding number in your first number, then the output of a less than b is set to 1. Circuit immediately determines the first number is less than the second number. If the two corresponding bits of your given inputs are equal, so then the circuit moves to the next bit position comparison. If that next bit position are also equal, then so here it will start that comparison till the least significant bit position. This process is continued till you have your last bit. Upon having that comparison, that circuit determines the first number is greater or lesser than the second number, or it determines whether the two numbers are equal. So if those two numbers are equal, it outputs that a equal to b is equal to 1. So we can implement this magnitude comparator with the use of your exclusive OR gates or exclusive NOR gates along with your AND and OR gate. Now a 1-bit magnitude comparator. So now let me design a 1-bit magnitude comparator here. So this 1-bit comparator is comparing 2 bits, is called as a single bit comparator. It consists of 2 inputs, each of 2 single bit numbers, and 3 outputs, which generates the outputs of less than, equal to, or greater than the inputs between the two binary numbers. So now the truth table for a 1-bit comparator is given below here. So here we mentioned the inputs a, b along with their 3 outputs a less than b, a equal to b, and a greater than b. So let me compare the comparison from started with the first combination a value with the b value. So only single bits, so hence the magnitude of a is 0, magnitude of b is also 0. So both magnitudes are equal. So a equal to b is 1, a less than b, a greater than b is 0. So 0, 1 where b value is greater than your a. So hence a less than b output is 1, a equal to b is 0, a greater than b is also 0. Next third combination, a value is 1, b value is 0. The relative magnitude of a is 1, b value is 0. Hence a greater than b, functional value of output is 1 here. A less than b and a equal to b is 0. Last combination, a value is 1, b value is also 1. So both are equal magnitude, only single bit comparison. So hence a equal to b is 1, a less than b, and a greater than b is equal to 0. Now if I am writing that output expressions, A greater than B is equal to A B bar, A less than B is equal to A bar B, and A equal to B is having the two minterms which are A bar B bar plus AB. So now it resembles, so almost it resembles A bar B bar is nothing but an exclusive NOR operation here. So this exclusive NOR, I can write it as A exclusive NOR of B. You can implement with the exclusive NOR, or we can also use the complement of exclusive OR of B. So this complement of exclusive OR of B is also equivalent to exclusive NOR operation. Now let me construct the logical diagram of 1-bit comparator. As A greater than B is output expression is equal to A B bar, and A equal to B output expression is A exclusive NOR of B. A less than B is equal to A bar B. Now we have taken the A as well as the B, and with the NOT gates we obtain the outputs of NOT gates. Each NOT gate is the complemented input. So here B is connected, so B bar, here A is connected, so A bar. So in order to obtain the A greater than B, we need to connect the input A with the B bar to the AND gate that produces the output of A greater than B. Next, to obtain A less than B, we need to connect A bar as well as with the B as the input to this AND gate. AND gate output will generate A less than B. Now to obtain the A equal to B output of magnitude comparator, both A and B are connected as input to this, so which implement the exclusive NOR function between the two inputs, which is A bar. For A bar B bar, your output function is 1. For AB values also, so the output functional value is equal to logical 1, since they are having the relative magnitudes are equal. So in the same manner, so we will also construct or realize your 2-bit magnitude comparator. Here 2-bit magnitude comparator consists total number of inputs on your comparator is 4. So each number is represented with 2 bits. So as A is represented with A0 A1, B is represented with B0 and B1. So let me check for your relative magnitude started with your most significant bits of your each number. So here first combination is 0 0 0 0, A1 0, B1 0. Then we will move with your till the last significant bit. So now the least significant bit is A0. So A0 is 0, B0 is also 0. Hence, so this will give you the output of A equal to B is 1 and A less than B, A greater than B is equal to 0. Next combination A0, A1 is compared with the B1. Both magnitudes are equal. Then we will move with the A0 with the B0. So A0 is 0, B0 is 1. So now B value is greater than your A. So A less than B output functional value is 1. A equal to B and A greater than B is 0. Next combination. So here, so the relative magnitude of A is 0. Relative magnitude of B is 2. So A less than B is 1 and A equal to B, A less than B, A greater than B is 0. Next, A1, A0 are 0, 0. So decimal code of this is 0. Here decimal code of B is 3. So B value is greater than your A. So hence A less than B output functional value is 1. A equal to B and A greater than B is 0. The same manner here, let me verify A1 with the B1 both are equal. So A0 is equivalent to B0. So in this combination, so A0 is 1, B0 is also 1, A1 is 0, B1 is 0. So hence A equal to B is 1, outputs of A less than B and A greater than B is 0. So upon determining their output functional values, so we have to write its SSOP expression of all the 15 combinations. So now if I write all the 15 combinations, then my output expressions are, so for that we are going to derive your each output functions for a greater than b, a less than b, as along with a equal to b. So now your a greater than b functional values 1 for a greater than b is for 4, next along with 8, 9. So next we also have functional values as your 12, 13 and 14. Now so here, so your a greater than b is equal to a greater than b. Now the SSOP expression of a greater than b is equal to sigma m of 4 comma 8 comma 9 along with 12, 13 and 14. So these are the SSOP expression of 4, 8, 9, 12, 13, 14 are your SSOP expression of a greater than b is equal to sigma m of 4, 8, 9, 4 we have mapped along with 8, 9, 12, 13 and 14. So now if I have drawn that K-map and minimized the expression, we obtain total 3 groups. In that 3 groups, one is squad, the remaining 2 are pairs. So now the squad can give you the minimal expression as A1 and B1 bar plus 2 pairs can form here. Here the first pair will give you A1 A0 B0 bar plus second pair will give you the product term as A0 into of B1 bar B0 bar. So minimal expression of A greater than B is A1 B1 bar A1 A0 into B0 bar plus A0 into B1 bar into B0 bar. The same manner, so your A less than B functional value is 1, or your minterms functional values of 1, 2, 3. So here let me write SSOP expression 1, 2, 3 along with we also have 6, 7 and 11. So 6, 7 and 11. So these are the minterms of your A greater than B, A less than B. So now, so for this A less than B, minterms are sigma m of 1, 2, 3, 6, 7 and 11. Let me map your function. Again, it also generates 3 groups. One is squared, 2 are your pairs. Squared can generate the product term as A1 bar B1 and these 2 pairs, first pair is generated with A1 bar A0 bar into B0. So second pair will generate the minimal product term of your A0 bar into of B1 B0. So these are the 2 minimal expressions of A less than B and A equal to B. So A less than B and A greater than B. Now let me write the SSOP expression for A equal to B is equal to sigma m of 0. Next we obtain the output functional value is 1. For A equal to B is 5. So 0, 1, 0, 1. Along with we also obtain the output functional value is 1 for 10. Along with we obtain the output which is 15. So 0, 5, 10, 15. So upon mapping 0, 5, 10, 15, these all are arranged diagonally. So let me write, so there were no minterms to pair it or no adjacency. So hence all are considered as a isolated minterm. So A1 bar, A0 bar, B1 bar, B0 bar is minterm M0. A1 bar, A0, B1 bar, B0 is your minterm 5. A1, A0, B1, B0 is minterm 15, and A1, A0 bar, B1, B0 is minterm 10. So now let me take A1 bar, B1 bar. So as your common variables, so if I am taking A1 bar and B1 bar, A0 bar and B0 bar plus A0 B0 from your first two terms. Second two terms, so let I take A1 B1 common and A0 B0 plus A0 bar B0 bar. So I can write this as, so A0 bar B0 bar plus A0 B0 is A0 exclusive NOR of B0, and this I can write it as A0 exclusive NOR of B0. So now A0 exclusive NOR of B0 and of A1 bar B1 bar plus A1 B1 is written as A1 exclusive NOR of B1. So output expression of A equal to B is obtained by doing the exclusive NOR operation between A0 B0 and A1 B1. So these two outputs of two exclusive NOR gates must be ANDed. That will generate your output functionality of your 2-bit magnitude comparator equal. So this is your basic logical diagram of your 2-bit comparator circuit with a 4 number of inputs A0, A1, B0, B1 and the 3 outputs. So now since A less than B is having 3 product terms, so we use the 3 AND gates with 1 OR gate that can implement A less than B, and the inputs which are connected for the first AND gate is A1 bar B1. Second AND gate is 3 inputs which transferred from A0 bar B1 B0. The third AND gate will have the inputs from A1 bar, A0 bar, B0. So generate your the A less than B upon connecting the outputs of these 3 AND gates to the inputs of your OR gate. A less than B is the output of your 2-bit magnitude comparator. In the same manner, A greater than B is obtained with the use of your 3 product terms. So hence we used here 3 AND gates. And in order to add these all the 3 AND terms, we are using the OR gate. That OR gate output generates your A greater than B. First AND gate inputs are A1, B1 bar. Second AND gate inputs are A0, B0, B0 bar as well as your B1 bar. Next, third product term is A1, A0, so and B0 bar. So generates your outputs, and these product terms are odd. Using the OR gate will generate the A greater than B. A equal to B is obtained by doing the exclusive NOR operation between your A0 B0, A1 B1. So and then these two exclusive NOR outputs are ANDed using a AND gate. So that generates your output of your A equal to B. So this is the design of your, this part of session will give you the design of your 2-bit magnitude comparator. In the next class we are going to deal with another circuit which is a combinational circuit of D.